In this video, I'd like to show you how we can derive an expression for the spring constant of a bending cantilever. So this is with reference to the AFM cantilevers that we looked at in the previous video, which get bent by a force as they come into contact with the surface, and we need to understand how that force will affect the way in which the cantilever bends in order to extract the force information and be able to use that to then image or measure forces with a surface. So in simple schematic form, we have a fixed point which has the cantilever coming out from it like this, and the cantilever is being bent by a force which is coming from interaction with the surface. We're going to say that the cantilever has a length of capital L, and then what we're going to do is consider a particular sort of elemental section within this cantilever, and we can show that that cantilever is going to have a deflection at a particular point of Z at a position X along the cantilever. Now it's important to mention that this calculation is only valid for really small deflections, but that turns out to be the limit that the atomic force microscope would work in anyway, and so is not really a big problem for us. But it won't work if we try to bend this beam too far. So I'm going to now try and sort of sketch a zoomed in version of this elemental section of the cantilever. So it's going to look something like this. Now, if I were to think about a plane at this point in the beam, as I bend this cantilever, you can see that this is going to get stretched, so that, you know, if this represents the unstretched elemental volume, then there's an additional bit that's been added here from the bending, which has put this whole region in tension. The same is true in reverse at the bottom here, that whereas I would have had a rectangular volume, by bending the cantilever, I've placed a plane down here under compression. It turns out there's an intermediate plane which has got a technical name, which is just the neutral plane. And here, because of the fact it's in the middle, it's neither under tension or compression. In fact, the stresses in this particular region are going to be zero. So we're going to do some calculations with reference to this neutral plane. If I do that, I need to define a few other variables. So we're going to think about a particular region of or a particular plane through our elemental volume, which is going to have a thickness dy, and is going to be located at a position y away from the neutral plane. In addition to that, we need to know how much the cantilever has been bent, and so there's this distance r, which represents the radius of curvature of the radius around which this cantilever is being bent. And then we also need to consider the angle theta that makes as well. So if we want to work out what the strain is, we need to work that out, how much additional stretch effectively is being put into this particular plane relative to a position that has no strain in it at all, which is this neutral plane. So we can write down that the strain in our elemental plane is going to be equal to the change in length of that plane relative to the neutral one, divided by the length of the neutral one. It's just a standard expression for a strain, is the change in length over the length. So if we think about this plane is at a position r plus y, and then it's got an angle theta that it makes. So in arc, we can use the expression for an arc in terms of radians here, and just write down that that plane, which is here, is r plus y times theta. We need to then get the difference, and the difference is relative to the unstretched plane. The unstretched plane is just going to be this distance r times theta, which will give us this length here. And then the same number that we've just calculated is L as well, so we can divide that by r times theta. So if we look at that, there's obviously some stuff that we can cancel out. The thetas can get cancelled, which gives us r plus y minus r over r, and r minus r disappears, which means that the strain in that volume is going to be equal to y divided by r. So that gives us the strain. If we want to turn that into a stress, we need to multiply it by the Young's modulus. So the stress is equal to the Young's modulus times the strain. So this is the Young's modulus here. And we just calculated the strain, so we know that the stress is going to be equal to EY divided by R. Okay, now the stress is equal to the change in the force divided by the change in the area. So if we want to do a bit of rearrangement, we can say that the change in the force is equal to E times Y over R. Then we can multiply that by dA. So I've just taken the stress, plugged that in here, and then rearranged it in terms of the change in the force. Now, in addition to calculating the stresses and the forces that are acting on that plane, there's also a moment that is being applied, a moment being a force times a perpendicular distance. If we think about, go back to this diagram here, the tension forces are acting in this direction, and then they are acting over a distance that is y away. So the moment that this stress plane applies to the neutral, around about the neutral plane, is just going to be equal to the force that's acting along this direction times the distance that that point is away from the neutral plane. So we can write down the moment that occurs as a result of the force that's in that plane, which we just calculated. So that's going to be dF times its perpendicular distance, which is y, which gives us E y squared over R times dA. So a bit of integration would then tell us that the total moment so this is the total moment just in this elemental volume, m is equal to E over R. Then we'd have to integrate over all the different planes, y squared dA, and that would give us the total moment. Now this little section here is a quantity known as the geometric moment of inertia, and you can find those for different shapes of solids with different dimensions, and it's not really necessary for us to calculate what that is. We can just look those up in tables depending on the shapes. So we can just substitute this value for I in for this integral, and we find that the total moment is just going to be equal to E times I divided by R. So that's great, but it just leaves us with some unknowns still. We don't really know what this radius is. We need to know what the curvature of the beam is in terms of things that we can work with more easily, like X and Z. So, question, what is the curvature 1 over R for this beam? Now, there's some kind of confusing language that's sometimes used around this idea of curvature. When we say the curvature, we actually mean 1 divided by r, whereas it might be, but then people sometimes talk about the radius of the curve, which is the value r. So try not to get these two things muddled up in your mind. It's a bit confusing, I know, but remember that when people talk about the curvature, what they're actually meaning is the 1 divided by r, whereas r is the radius of the circle, which is formed by that curve. So how can we work out what that curvature is? Well, if we draw ourselves a sort of more simpler version of the cantilever here, we're going to have a section that we're interested in, which is r away from the centre of the circle, and then we've got some angle here, d theta. There's a section of the arc which has a length dl, which corresponds in the horizontal direction to a length dx. And this is the first time we're going to use those small approximations. So what we're going to say is, if you think about this triangle, it's dx long and dl long on this side, and then there's some small angle in here. So to work out this strictly, we'd have to use the cosine. So we'd say that cosine theta is approximately 1 minus theta squared over 2. Now this is using radians, but if we were to work out on our calculator what is the cosine of 5 degrees, let's say, you'd get something that's about 0.996. So to all practical intents and purposes, when we do the trigonometry here to work out how dl relates to dx, they're going to be different by some very, very small amount. And so we can simplify this by just saying that dl is basically the same thing as dx, as long as the angles are reasonably small. And what that means is that this arc length, dl, which was equal to r d theta, is also the same thing as dx. And then as a result of that, we could rearrange this and find that 1 over r is going to be equal to d theta by dx. Now, we haven't quite got there yet, because d theta is also not a very useful variable, so we now have to ask the question, well, what is d theta? So one of the ways to try and think about what is going on with d theta, how we calculate, d theta by dx, is to think about this curve. If we want to try and calculate the gradient at different points, we might draw little triangles on here like this. Each of these triangles would have some length, dx1, dx2, and it would have some drop, which would be dz1, dz2. Now, the angles that are going to be going on here come from the fact that we've also got angles coming from here. This is going off to the centre of the circle. So if we want to work out those angles, we've got an angle theta with respect to the vertical here, but we've also got an angle here of theta plus some small incremental change that's happened along this direction. So these angles are the same angles as up here. So here we have theta, and here we have theta plus d theta. So we can obviously write down an expression for theta now here in terms of this gradient change here, which is just dz by dx. And if we wanted to work out what d theta by dx was, we could then differentiate that to d2z by dx squared. but d theta by dx was what we were trying to work out. So we can now write an expression for the curvature as basically being approximately equal to d2z by dx squared. Now, you have to go back quite a long way to find this. We worked out what the moment was in terms of EI and this 1 over r that we didn't know. So we can now write down that the moment of inertia for this elemental volume is going to be equal to E times I times d2z by dx squared. Okay, so this is trying to work out the moments of inertia that are, the moments that are occurring internally to the beam as a result of this bending. This beam is obviously being bent by an external force, which is also applying a moment to the whole structure. So in order for this cantilever therefore to remain static, there must be an equilibrium between the external applied moment to this beam and the internal moments which are effectively resisting the bending. Now the external moment is rather simple, because if we again draw structure down here, here's a force being applied to the end of the cantilever. We're interested in considering this little elemental volume here, which is a position x from the fixed point, and the cantilever we know has a length L. So again, the moment is just the force times the perpendicular distance, and this is obviously therefore going to be L minus x. So as well as being able to write down the internal moments, the external moment, which must equal that, is going to be equal to the force that we're applying to the end of the cantilever times the distance in the perpendicular direction to the volume that we're interested in. So yeah, perpendicular distance. Okay, so as we said, that both those two things have to balance in order for the cantilever to remain static, which means that EI d2z by dx squared is going to be equal to F times capital L minus x. I can rearrange that in terms of the d2z by dx squared. It's going to be equal to F over EI times L minus x. Now what we need to do is try and integrate with respect to x, so we can get an expression for z in terms of x. And we'll do that one at a time. So the first integration with respect to x clearly turns d2z by dx squared into dz by dx. That equals F over EI, and the integral of L goes to Lx, and the integral of x goes to minus x squared over 2, and then because we've done it implicitly, you've then got an integration constant. So what are the boundary conditions on this problem? We know that at this point here, where the cantilever meets the wall, that x must equal 0, I'll do that down the bottom there. We know that x equals 0, z equals 0, and perhaps maybe not quite so obviously, the gradient also here must equal 0. So we could also write down that dz by dx equals 0. So plugging those numbers into this equation, we've got that 0 equals F over EI times the bracket, and then both the x terms are going to be 0. So 0 equals C1, which means that C1 must equal 0, and therefore we can get rid of that. Having done that, we can integrate for a second time, and then we find that z is going to be equal to F over EI times Lx is going to go to Lx squared over 2 minus x cubed over 6, 3 coming down there. And we again get a constant of integration. But for the same reasons as we saw here, because z equals 0, we have 0 equals, the bracket goes to 0, which means that C2 must also equal 0. Then what we can do is we can try a different boundary condition, and we can set x equal to L. So at x equals L, we're looking at the elemental volume that's right on the end of this cantilever, and we know that there's a force acting on that cantilever, and so what we can do is write down Z is equal to F over EI times, then we've got L times L squared, so that's L cubed, over 2 minus L cubed over 6. A little bit of simplification there. To combine these two gives us that F over EI is going to be equal to simply L cubed. In fact, that's a bit unnecessary. We'll stick that back in there as an L cubed. And then from the bottom here we've got the 3 from combining the 2's and the 6 there. So if we rearrange this expression in terms of F, we end up with F is equal to 3 times E times I divided by L cubed times Z. And hopefully you can see that we have something that looks a bit like Hooke's law here. So F equals KZ. What we have here is the same as the K, and so we can write down an expression for the spring constant, which is what we're after, of the cantilever, which is going to be 3 times E times I over L cubed. That gives us our final expression. So what we've been able to do is, by just thinking about the geometry, figure out what the spring constant is in terms of the fundamental properties of the cantilever. Its geometry, which is effectively specified by its length and its rotation, its geometrical moment of inertia, and also E, which is its Young's modulus.